Japan, the high winds, the rain, the treacherous torrents of the waters within the straits of Akashi, all of those features had to be accommodated in design and in construction.
The channel between the anchorages was deep and gravel-lined with bedrock far below the point where excavation for tower foundations would be practical. But the builders wanted to find the most stable surface possible, and these towers would be the biggest in the world at 930 feet in height. The solution would involve setting a huge steel cylinder known as a caisson onto the gravelly bottom to provide a strong, stable footprint for each tower.
The caissons are approximately 65 meters or so below sea level, and they are approximately 80 meters in diameter. They're huge. The Japanese had to accommodate, number one, the tidal currents, which were as much as 4.5 meters per second. What they decided to do was to actually prefabricate huge double-walled steel caissons, two of them, one for each tower. And they built those steel caissons on the fabrication plant.
Each 19,000-ton caisson would be sunk and filled with concrete to supply a firm base. But resting on gravel introduced other problems, such as scouring, where the swift currents would wash out the gravel beneath the caisson.
Since I knew that the prevention of scouring was the greatest challenge, we conducted laboratory tests with 1/100 scale models for almost 3 years. As a result of the test, we determined that the anti-scouring measure would be to install 80-meter wide ripraps around the caisson.
Riprap is a term from mounds of large rocks, which would surround the caisson on the sea floor. First, the sea floor would be dredged using a traditional floating dredging unit. Then, once a circular hole was made, the caisson could be sunk. The rocks, or riprap, would be dropped around the caisson. But there was still a problem.
With stones of that size, the sand between them would get sucked up. To deal with that problem, we came up with filter units.
These filter units were bags of smaller rock that would sit atop the other stones, forcing the water to flow through them. This either diverted or slowed the flow of water to the point that the scouring or removal of seabed was practically eliminated. The caissons would be able to sit on a gravelly bottom without losing their footing and twisting out of position. Tests showed this approach to be sound. Now the caissons had to be completed and towed into position for sinking.
The caisson, which is 80 meters in diameter, is divided into two sections, the double wall and the inner core. The area of the inner core is about 2,500 cubic meters. We conducted training for the submerging process at Shodo Island for about a month. Then we picked a day with the smallest current to tow it there. As I said earlier, this caisson has a double wall. That became the buoyancy tank, which made it possible to float.
The enormous caisson was ready to head out to the choppy seas of the Akashi Strait. It would be the largest structure of its kind ever towed through these waters, and would face the dual threats of fierce winds and driving seas. Central Japan, the turbulent Akashi Strait. On a clear March day in 1989, 12 powerful tugboats began the perilous job of towing the giant caisson, the first of two to the job site. Once it was centered over the prepared seabed, special cables were connected between the caisson and numerous huge anchors on the seafloor. These anchors have been dropped in a circle around the prepared pit in the seabed and would help to guide the caisson into the proper position as it sank.
We pulled out a cable from the winch on the top of the sinker, or anchor, which was already on the seabed, almost 1,000 tons each, and connected it.
This was quite an achievement in itself because you have effectively a cork bobbing in the water and you're trying to hit a perfect spot, and through the use of GPS and positioning systems and ballast and weight, they slowly could sink that caisson down to the prepared seabed.
翌日の
We started the submerging process the next day at low tide. The submerging work was done by pumping seawater into the core part and lowering it straight down. There was a monitor on the caisson, and we measured the positioning of the caisson and maneuvered the cables. Then, about 1 meter from the seabed, we sank it with about a 2-centimeter error.
The huge caisson now rested on the seafloor. Soon the other one at the south end of the channel would follow. Now, final preparations had to be performed on the silty muck that they covered.
それで
There were some more residues that the grab excavation could not pick up. After submerging the caisson, we used an underwater robot called Airlift to suck up some rocks and rubble.
But once firmly on the bottom, the huge can had to be filled with something other than seawater to make it heavy.
Once that caisson was in place, all of the water was pumped out and it was replaced by special underwater concrete.
This was a new way of doing business for bridge builders. Traditionally, caissons have been sunk, pumped out, and then men sent inside to work. Danger was a constant companion, and many perished. But this caisson had been sunk onto a prepared seafloor, and the only thing entering it would be this special concrete. But because the entire structure would be submerged, the Japanese needed a concrete that could settle and cure underwater. Enormous concrete plants were floated to the caisson on barges.
The ingredients were mixed and then pumped in to displace the water.
Each layer poured used up most of the raw materials on the barge. As this mixture hardened underwater, the construction crews would wait for the next favorable tide. The average wait was 2 weeks.
Ultimately, that whole 80-meter diameter caisson, which is about 70 meters high, was filled completely with concrete. And then a special table or top was placed on that caisson, about 10 more meters of concrete, into which was anchored the tower bases themselves. Once the steel tower bases were cast into that tabletop, then the erection of the towers began.
The height of this tower is about 300 meters, 1,000 feet. One of the most important issues for the design of this tower is wind-resistant design. Because the tower is very high, so it is relatively flexible and easy to vibrate due to the wind.
Many tower designs were considered. The design chosen was a so-called cruciform, where X-braces would support the openings between the vertical supports.
The purpose of that is really for aerodynamic stability. It was the most forgiving shape to accommodate the strong forces of the very strong winds that occur.
The tower design also had to incorporate one more major design component. The two towers had to be able to withstand Japan's frequent and often mighty earthquakes.
From a seismic point of view, it's primarily the towers. That's the next, the most critical element, because the towers support the cables. If there are failures, we could see the towers getting overloaded, local buckling of the steel towers at the base. These are the kind of critical conditions we are designing these structures for.
Each of the 930-foot high towers was prefabricated at one of 12 factories across Japan. They had to match each other perfectly. Cooperation was critical. Tolerances needed to be very precise to assure a truly vertical structure.
Tower one shaft consists of 30 blocks vertically. Both sides of the blocks are polished. Because one of the most important things for the tower is vertical accuracy.
Each tower component was hauled to the worksite by a huge barge-mounted crane.
We use a large tower crane with a capacity of 160 tons, and with that crane we put each block by block.
The slightest deviation would be magnified as the towers reached skyward.
The tower must be perfectly vertical, so you do not induce extraneous forces into the tower as the cables pull one way or another on the towers themselves. What that translates to is about an inch out of plumb over 900 feet high. So in order to achieve that accuracy, tremendous tolerances had to be met. They were perfectly matched so that when you put one on top of the other, that mating surface is absolutely perfect.
As the construction progressed, the engineers were required to check the fit on each side of each block of the tower.
Feeler gauges, little shims were used, and the acceptance was that you could not put that shim or feeler gauge between the mating surfaces of one block when stacked on top of another.
In essence, the clearance between the tower blocks had to be thinner than a playing card to pass inspection. If not, the block would have to be returned to the factory to be further refined. But none were. The workmanship was that precise. The weather, however, was not so accommodating.
That was a thunderstorm. In December of 1992, the northern tower was almost completed, and this southern tower is about 200 meters high or something. And that time there was a very large thunderstorm. It broke the measuring equipment on the cranes on the northern tower, and we have to stop the construction work about 3 weeks.
In fact, between heavy rain, typhoons, and rough seas, construction was able to progress only about 6 days in 10. But this had been factored into the schedule, so the overall delay was minimal. Soon, the towers soared gracefully into the skies above the Akashi Strait. But there was one more important device used to ensure they stayed there.
We decided to put the tuned mass dampers inside the tower. This is one of the most important things for these towers.
Tuned mass dampers are huge weights that counteract the forces of wind or high loads on the bridge. With constant input from computers, which are in turn wired to sensors throughout the bridge, the tuned mass dampers can be set to rock in a direction and at a frequency that will offset the sway inherent in such tall towers. 20 were installed in each tower and worked 24/7 to keep the structures upright. With the giant towers complete, the next gargantuan task loomed before them: stringing the 3-foot diameter steel cables.